Hi, my name is João Carlet. I'm here on behalf of the University of São Paulo. We have this project for developing assistive technologies. And by we, I mean the São Carlos School of Engineering and the Bauru School of Dentistry. This work is part of this project, and it's called a hearing aid development platform for simplified algorithm development. The motivation for it is the high demand for assistive technologies in low and middle income countries, such as Brazil, and the high prices of those technologies. The objectives of this were to implement a circuit board and a development framework that is easy to use and that uses and that relies on open source and open access tools and small and power restricted components. Hearing loss is a global health issue. It affects around 1.5 billion people worldwide, and this number is expected to rise to 2.5 billion people up to 2050. It's associated with a bunch of health outcomes, such as cognitive decline and reduced quality of life. In Brazil, 26% of the population has some sort of hearing loss, and about 14 million needs hearing aids. We have the Unified Health System, SUS, that provides only 30% of the demand of hearing aids. The biggest problem with hearing aids is their high cost and the limited public funding. While there are a few open source solutions in the literature, most of them are power hungry and bulky, and often they're really hard to use because they rely on C programming. And there is this clinical and technical divide between the engineers who have the programming skills but lack the clinical tools, and audiologists that are the opposite. So we thought a collaboration between those two would be very useful for enhancing innovation. That's why we presented Tiresias, which is our hardware platform that uses both Bluetooth SoC microprocessor and separated audio DSP. The SoC we use is the NRF5340 from Nordic. It has Bluetooth 5.4 and supports FPU and Auracast and all of those technologies from Bluetooth. And by using the ADAU, we can outsource the audio processing from the microcontroller. The advantage of doing this is not only the power consumption that goes down, is also that we can use the Sigma Studio, which is this development framework from Analog Devices that has a bunch of DSP blocks that you can only drag and drop and test your algorithms. Moreover, we use microphones, voice pickup sensor, an inertial measurement unity from Bosch, flash memory, power management IC for rechargeable batteries, and a bunch of connectors and test points. For the development tools in the Nordic, we use the NRF Connect SDK, which is based on Zephyr real-time operating system. It's programmed in C, and it has a bunch of modular libraries and all the advantages of using real-time operating systems like task scheduling, and also has a bunch of built-in device drivers and guided user interface that can be especially useful for prototype. For the DSP development tool, there is the Sigma Studio, which, as I said, has a bunch of fixed function DSP blocks. You can drag and drop compressors, digital filters, equalizers, and also a bunch of tools for simulation and debug. As an illustration, we have this simple setup, which uses a Focusrite Carlet interface and ADAU 1787 evaluation board. I hook the output of the interface to the input of the ADAU and the output of the ADAU to the input of the interface, so that the interface can characterize the algorithm run in the ADAU. We have two example applications here. The first is the headphone target response, frequency response. It's based on Sean Olive work in the Audio Engineering Society. As you can see here in Sigma Studio, I'm using a graphical equalizer with some gain and some filters, and I'm running some tests in real. The outputs of the tests are gonna be in dB full scale, so it's only a relative measurement, but as you can see, the result is very similar to what we saw in Sigma Studio and very similar to the frequency response we wanted. And the other example is a NAL revised profound prescription that we done based on Biscard audiograms. It's a standard audiogram letter E. For this example, I used a bunch of digital filters and gain blocks. All the digital filters were set according to the prescription and then fine-tuned. You can see here the simulation probes and the simulation stimuli. And these are the outputs for the simulation. And we're gonna check with the measurements in real, in dB full scale. Here we are running the test. And as you can see, we have a response very similar to the simulation and very similar to what we wanted with our prescription. Moving forward to the hardware architecture, we connect the SoC to the ADAU, and they communicate using I2S for audio and I2C. In the I2C duct, we also communicate to the inertial measurement unity, and via SPI, we communicate to the flash memory. The power management IC is controlled by the NRF and distributes the battery power to the rest of the printed circuit board. The MEMS microphones and the voice processing unity, as well as the audio output connector, are connected to the DAU. The printed circuit board has a 25 by 40 millimeter footprint, which is very similar to a LiPo battery, and it's open in GitHub. You can see all the hardware files there. For connectivity, we have two audio outputs, a battery and an external power inputs. And for debug, we use the serial write debug. Here you have a shoot around on the hardware file, an Altium designer. Here you can see the two MEMS microphones. This is the ADAU. You have also the oscillator for the ADU. In the center, we have the SoC, the flash memory there, the IMUs and buttons, LEDs. Going to behind, you see the audio outputs and the VPU on one side. The other side is all for power and debug. We also want to implement a custom chassis, which is supposed to use two PCBs, one each of the user temples, which are going to be connected to in-ear headphones or custom earpieces. And for software tools, we want to implement a desktop and a mobile app together with a Bluetooth framework so that you can tune parameters over the air and update the firmware over the air, as well as communicate between PCBs with audio. We also want to run some tests with the IMU together with electrophysiological sensors. And we also want to implement sound scene classification scheme, which is going to be presented here at VCCA as well. We need to acknowledge the University of São Paulo for granting this project and the National Council for Scientific and Technological Development for paying our scholarships. We need to acknowledge both Analog Devices and Nordic for providing us with development kits and institutional knowledge. That was our presentation. I thank you very much for watching it, and we are now open to questions. Thank you.